Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics. We are going to discuss about operational amplifiers, in which active filters, types of filters, analog computers for solving simultaneous equations and second order differential equations. What is a filter and what is an active filter? A filter is an electronic circuit which allows selected band of frequencies and attenuates the frequency signals outside the band, and that is a filter. And what is an active filter? If a circuit has an active component like an amplifier, then it is an active filter. So, it is another application of operational amplifier by which we are going to filter the input signals. So, what are the advantages of the active filter over the passive filter? If you have an amplifier in the filter circuit, the gain of the amplifier can be adjusted and the inductors need not to be used in the circuit, and which is very bulkier and which is very expensive also. And if you have an operational amplifier in the filter circuit, the loading effect can also be minimized, the loading problem can also be minimized, and cost also reduced. These are some of the advantages of active filter. This is the frequency response of all the filters. From the frequency response of the circuit, you can say this response is for which filter. The first is for a low pass filter. When you see the graph, this is the lower range of input signal. In x axis, frequency of the input signal is plotted, and in y axis the gain of the filter is plotted. And here this is the lower range of frequencies up to this cutoff frequency. This frequency is said as cutoff frequency, and up to this cutoff frequency all the signals are getting passed by the filter, and after this cutoff frequency it is attenuated. So, the gain is decreased. So, this response is for low pass filter, and the reverse of this response is high pass filter for high pass filter. This is the cutoff frequency. Up to this cutoff frequency there is no signal passed by the filter, and after this cutoff frequency all the signals are getting passed, and so this is the response of high pass filter. And this is band pass filter, and here this is the band stop filter. For the band pass and band stop, we have two cutoff frequencies. One is lower cutoff frequency and next is higher cutoff frequency. In center it is the center frequency. So, for band pass, in the center frequency you got the maximum peak for the gain, and up to the lower cutoff frequency no signal is getting passed. After the higher cutoff frequency also no signal is getting passed, and between these two cutoff frequencies all the signals are passed. And here band stop filter, for this particular band the frequency is stopped or attenuated. Outside this band all the frequencies are passed by the filter. These are the frequency responses of all the types of filters. And here this is the circuit of the low pass filter, in which there is an amplifier IC 741 is used, and here the negative terminal is grounded through the resistance R1, and to the positive terminal only we are giving the signal through RC network, and this is said to be the filter circuit. Now, after passing through this circuit, the voltage at this node is the input voltage given to the positive terminal of the amplifier, and the output is getting here. So, the cutoff frequency is selected or decided by these passive components, right. So, R3 and C1 is the major factors for selecting the cutoff frequency of this low pass filter. When you see this frequency response of the low pass filter, this is the cutoff frequency. For the low pass filter, the cutoff frequency is called as higher cutoff frequency, because up to this higher cutoff frequency all the signals are passed, and outside this higher cutoff frequency no signal is passed, right. So, we have to derive the cutoff frequency now. Before that, you have to know the relationship between the frequency and the capacitive reactance. So, it is inversely proportional. The frequency is inversely proportional to the capacitive reactance. If the frequency is very high, the capacitive reactance is very low, and if the capacitive reactance is very low, what happens to the capacitor, the path of the capacitor? It is shorted. If it is low, it is shorted, and if the frequency is low, the reverse, capacitive reactance is high and the capacitor is opened, the path of the capacitor is considered to be opened. And if you see the passive filter or see, suppose Vi is given here, and what is the voltage across the capacitance we are going to see now. According to the relationship between the capacitive reactance and the frequency, if the higher frequency signal is given, what happens to the capacitance here? If higher frequency is given, the capacitance is reduced, the capacitance effect is reduced. So, C is shorted. So, if this path is shorted, then there is no output across the capacitance. So, the output voltage is 0 for the higher frequencies, and if the frequency is low, the capacitance is opened, the path of this capacitor is opened, considered to be, right. So, if the lower frequency signal is given, this path is opened and the frequency, all the frequency is taken across the output terminal. Okay. So, this is the circuit for the low pass filters. For lower frequency, all the output will be, all the input signal will be taken across the output terminal. That is why this is said to be low pass filter. For the reverse, if the capacitance is in series arm and the resistance is in shunt arm, suppose you are going to take the output across the resistance. Again, if the frequency is high, C is shorted. So, this loop is shorted, and what is the output now? If this is shorted, then the output is whatever voltage is given, the same voltage will be obtained at the output. If the frequency is low and the capacitance is opened here, and what is the output here? If this is opened, then there is no path between the input and this node. So, no voltage will be obtained at the output. So, this is for the higher frequency. This combination of the resistance and capacitance will produce the voltage, whatever the input voltage is given, the voltage we can take it at the output. So, this is said to be high pass filter. For the lower frequency, the output will be 0. So, this is the setup of the low pass filter and the high pass filter, and now we can derive the transfer function of the filter. So, we are giving the signal to the positive terminal, and so the negative terminal is grounded. Say this is R1 and this is RF, this is V0, and through the setup RC network, we are giving the input signal to the filter. So, what is the voltage at this node? Say this is VA. So, we have to calculate what is VA now. VA is the voltage across the capacitor. So, VA into 1 by Cs divided by the total R plus 1 by Cs. So, it is Vi by Cs divided by RCs plus 1 by Cs. This will get cancelled. And what is the output now? V out is equal to the gain of the amplifier into VA. So, gain into what is VA? It is VI by 1 plus RCS. So, from this the transfer function of the circuit, the total circuit is written as V naught divided by Vi is equal to A by 1 plus RCS. Now, if you put S is equal to j omega, and here everything must be in S domain. So, if you put S is equal to j omega, and if you take the mod value of this transfer function, say it is h of j omega, you will be getting 1 by 1 root of 1 plus j, instead of omega if you put 2 pi f, it is 2 pi f r c, and again if I make this as the whole square also, j into f by f h the whole square. So, here this is the transfer function of the low pass filter. It is obtained as root of 1 plus j f by f h the whole square. Why it is f h? Because the low pass filter has always the higher cutoff frequency, because after this frequency all the signals will get attenuated. So, now we have to see the relationship between f and f h, and here what is f h? From the equation, this f h is the higher cutoff frequency, it is decided by 1 by 2 pi r c, these terms 1 by 2 pi r c, right. So, now f is less than f h according to the formula. What is the formula? Transfer function of the filter is A by root of 1 plus j f by f h the whole square. So, according to this formula, if f is less than f h, f is less than f h, we can assume this total value f by f h is less, and so we are assuming it as 0. So, the transfer function, this gain, or you can say the gain of the filter is just A, right. And for the second case, if f is equal to f h, if it is equal, then the gain will be given as A by root 2. If both the frequencies are equal, it is A by root 2. And for the third case, if f is greater than f h, if f is greater than f h, this total term is this f is very high, and so the gain A will be reduced at the rate of minus 20 dB per decade. So, now for this relation of the input frequency with the higher cutoff frequency, we can have the response of the low pass filter. So, for the first case, f is less than f h. So, for this value, f h is the higher cutoff frequency, say this is the cutoff frequency, or it can be the corner frequency f c, right. So, up to this f c, f is very low. So, what is the gain of the transfer function of the filter? It is A. So, the frequency response, in this frequency response, the gain is maintained as constant, and say this is A. This particular value is A. If f is equal to f h, then we derive the transfer function of the filter as A by root 2. So, this is minus 3 dB, that is said to be A by root 2. So, this is the corner frequency. So, here the gain is reduced by 3 dB if you calculate in dB. So, it is A by root 2 normally, and if f is greater than f h, the gain of the filter is getting reduced at the rate of minus 20 dB per decade. So, this is the frequency response of the first order low pass filter. We have a break now. Welcome back. We have seen the first order low pass filter, and this is the frequency response of the first order low pass filter. So, for the first order, the roll off rate of the gain for the gain of the filter is only minus 20 dB per decade. If you go for the second order, then the slope, the reduced rate is minus 40 dB per decade. If the orders are increased, then the roll off rate is increased by 20 dB. So, for the second order low pass filter, you have to use the RC networks, 2 RC networks in the input path. So, here this is one RC network and this is another RC network we have used, and we have derived the transfer function for single order low pass filter as 1 by 2 pi RC, and the gain, we know that the signal is given to the positive terminal. So, always the gain is 1 plus the feedback resistance divided by the input resistance. Here the feedback resistance is R2 and the input resistance is R1. So, it is 1 plus R2 by R1. So, these are the two formulas you have to note it down. For the second order low pass filter, the corner frequency, or you can say this as higher cutoff frequency, it is derived as 1 by 2 pi root of R3 R4 C1 C2. Here it is R3 R4 and C1 C2. So, if these values are equal, then you will be having 1 by 2 pi RC. What will happen if you cascade the filters? If you cascade the filters, the gain of the filter will get multiplied. So, for example, if the first filter has the gain 10 of the gain of the amplifier, and the second one has 32 and the third one is 100, then the gain of the total circuit, the gain between the input and the output, otherwise V out by V in is equal to the product of all the gain of each and every amplifier. So, 10 multiplied by 32 multiplied by 100, you will get 32,000, and in dB you have to add the gain of the filters individually. So, it is 20 dB plus 30 dB plus 40 dB. So, it is totally 90 dB. So, again the first order high pass filter. So, for the high pass filter, this RC network, it is just reversed. What you have in the low pass filter is you have a resistance here at the series arm and you have a capacitor at the shunt arm, and the remaining all the connections are the same as in the case of the low pass filter. So, here the input signal is given to the positive terminal and the feedback is given to the negative terminal. And again the gain you have to calculate it as 1 plus R2 divided by R1, and you have to calculate what is the frequency, that is the lower cutoff frequency for the high pass filter, and it is decided by these two passive components R1, R3 and C1. And this high pass filter will pass the signals after the cutoff frequency and it stops the signals below the cutoff frequency. So, for the high pass, you know the circuit. In the series arm you have a capacitor and here you have a resistor, the passive network input side present in the high pass filter, and the signal is given to the positive terminal and negative terminal is grounded through the resistor R1. This is V0, this is R2, R1. So, again this is the voltage given to the positive terminal of the operational amplifier. Calculate what is VA, it is the voltage across the resistance. So, R into VI divided by the total R plus 1 by CS, it is R CS divided by R CS plus 1 into VI. And what is V0? The gain of the amplifier into the input voltage VA. We know that VA is VI RCS divided by RCS plus 1. If you take it is A, again if S is equal to j omega, here it is A into R C j omega divided by 1 plus j omega or C, and you have to take root here, this whole square, and omega is equal to 2 pi f. You will be getting the transfer function of the filter as A into j f by fl divided by 1 plus j f by fl the whole square root 2. So, here fl is nothing but 1 by 2 pi r c. Again h of j omega is f by fl divided by root of 1 plus j f by fl the whole square. Again, if f is less than fl, if f is less than fl, what happens to the gain of the filter? That is h of j omega. If f is less than fl, this product, if f is less than fl, then the total gain is very low, and if f is equal to fl, these terms will get, this will be equal to 1, and so it is equal to a by root 2, and f is greater than fl, the gain, if f is greater than fl, this is also greater. So, both will get, and this will be neglected, this one will be neglected when you compare it with this term. So, this will be cancelled out and you will be having the gain as A. So, the frequency response is, here in x axis you are taking the frequency of the input signal, and in y axis gain in dB. So, for the frequency, for the first case, if f is less than fl, say here it is fl. So, up to here, if f is less than fl, the gain is low, so it is increasing, and if f is equal to fl, at this point the gain is a by root 2. So, here it is root 2, this point a by root 2, that is 3 dB lesser than the maximum gain if you take it in the dB scale, and if f is greater than fl, your gain is maximum. This is minus 3 dB line, and this is maximum, this is the pass band, this is A, this is the frequency response that is given here. So, this is said to be stop band. Initially, for the high pass filter, for lower frequency signals, say this is an example for the cutoff frequency 1 kilohertz. So, below 1 kilohertz for all the frequencies it stops, this is the stop band, and above 1 kilohertz all the frequency is getting passed through the filter, and so this is the pass band. And this roll off rate, that is the gain is slowly increased at the rate of plus 20 dB per decade for the first order high pass filter. And if it is for second order filter, you will be having the 2 RC networks in the input path, and this roll off rate will be increased by another 120 dB per, another 20 dB per decade. So, every order the increase in rate is plus 20 dB. This is the second order high pass filter. So, another 2 RC pairs in the input path, and the gain is always 1 plus R2 by R1, and the frequency, the cutoff frequency or the corner frequency is derived as 1 by 2 pi root of R3, R4, C1, C2 as per the circuit. If you cascade the filters, first order filter the roll off rate is 20 dB per decade, second order filter if you cascade 2 RC networks, then you will have the roll off rate as 40 dB per decade, third order is cascading first order plus second order. So, you will be having the roll off rate as 60 dB per decade, and so on. Next is an electronic analog computation. So, it consists of this electronic analog computation consists of the addition, subtraction, integration, differentiation, inversion, scale changer, So, all these computations can be simply represented as, for this grounded part schematic. So, it is less than 1 kilo ohms can be multiplied with the input signal. So, it is represented as x into k. So, that is the output here, kx. So, this is a symbol of the potentiometer, and here this is a inverter because these two resistors are equal. So, the gain is 1 and the input signal is always taken at the output here, since the gain is 1, and it is symbolically represented as 1 here and simply a triangle to which input is given and output is taken. And if instead of 1, if you put G, then there is a difference between the values in the feedback resistor and the input resistor, and here G is the resistance ratio RF by R1. So, there is a difference in the values of the resistance here. And when you come back here, these are the input signals given to the summing amplifier, and G1, G2, G3 are the gain of the amplifiers, and here the output of the filter will be, that is E1 is amplified with G1 plus E2 is amplified with G2 plus E3 is amplified with the factor G3. That is the output you can taken from this symbolic representation. So, this is the summing amplifiers of 3 input signals symbolically given here, and this is the integrator. For this integrator, the symbol is, there is a rectangle box followed by a triangle box. Here this G is given as 1 by RC, where R is the input resistance and C is the feedback capacitance in the circuit. So, this is the symbolic representation of an integrator, and here summing integrator. So, here if you see the rectangle box at the first stage of the symbol, then it is a integrator. If it is not so, then it is an amplifier. So, E1 is the signal integrated with the time constant G1 plus E2 is the signal which is integrated with the time constant G2 plus E3 is the signal integrated with the time constant G3. That is the output you can taken at this symbol. So, based on this, if you want to calculate this value x1 plus x2 plus 10 x3 plus 10 x4, you have to give x1 x2 directly. For these two inputs, the resistors of the input resistor and the feedback resistor will have the same value, and for this signal 10 x3, the feedback resistance is 10 times of the input signal also for the next input. So, here the gain factor is given as 10 for x3 and also for x4, and what about x1 x2? It has the unity gain. So, it is represented as 1 1. So, here when you see the input side of the triangle, there is no rectangle box. So, it is an summing amplifier. So, the output is the sum of all the inputs which is amplified by the corresponding amplification factor. This is said to be summer amplifier. So, based on these symbols and these mathematical operations, you can derive the simultaneous equation as well as second order differential equation. To summarize the class, we have seen low pass filter in which first order filter, second order filter, high pass also, high pass filter in which first order filter and second order filter we have seen, an electronic analog computer by which the addition, subtraction, integration, all these mathematical operations can be symbolically represented, and from which you can derive the differential equation, also the simultaneous equation. Questions: list the advantages of the active filter, list the types of filter, what are the operations performed by the electronic analog computer. These are the references. Thank you.